All right, there's one last topic we want to cover for this section, and that's the relationship between energy and chemical reactions. So without further ado, let's get right to it. And they have changed my interface, so this is going to be an interesting get right to it. All chemical reactions involve a change in energy. Chemical bonds are a form of potential energy, remember. So to break them requires energy, and when a chemical bond forms, it releases energy. Not only that, but in order for a chemical reaction to occur, the molecules have to collide. They have to meet, they have to come into contact. And whenever things come into contact, that involves exchange of energy. All chemical reactions involve a change in energy. Therefore, every single chemical reaction out there has energy as a factor. And we're going to look at the impact of energy on some chemical reactions. Let's take a look at a very simple chemical reaction. The reaction of hydrogen with iodine. So we've got hydrogen here, and we'll make it the green, and we've got iodine here. First of all, in order for them to react, they have to collide. That collision gives them energy, or releases, well, it gives the molecules energy, which they use to break the bonds. And once those bonds form, energy is released. The vast majority of the time, and we're talking 99% up, bond breaking requires energy, bond forming releases energy. And you can think about this in terms of your own life, right? Because think about when you break up with somebody, right? When you break up with somebody who you've been in a long-term relationship with, what do? You grab the Chunky Monkey ice cream, the Rocky Road. You eat every carbohydrate you can ever find on the face of the planet. You feel drained, you're tired, you're moping around, right? So breaking up requires energy. But what happens when you form a new relationship, right? You got that puppy love going on. You feel euphoric, right? You feel like you've got all the energy in the world. You're singing and dancing like you're in a bad episode of Glee or something, right? So forming new bonds releases energy, just like forming a new relationship does. Breaking up requires energy, just like breaking up with somebody does. So what we can see here is that chemical reactions involve changes in energy. Now, not all collisions between molecules result in a chemical reaction. In order for two chemicals to react with each other, they have to collide with a minimum amount of energy. The minimum amount of energy required for a reaction to occur is referred to as activation energy. We're familiar with the concept of activation energy and chemical reactions in our everyday life. After all, if we want to start a fire, fire produces energy, right? We can feel the heat coming off of a fire. But in order to start a fire, we have to provide the fire with some activation energy, right? When you take a match, that match isn't spontaneously burning by itself. You have to provide it with activation energy by striking it against something. So you have to give it some energy. That energy that you have to give to get the reaction started is referred to as activation energy. Not every single chemical collision will result in a reaction if it doesn't have that minimum activation energy. You can also think of this in terms of dating, right? When we say that we've got love with somebody, we say it's because they had that special spark, right? I wish I had $1 for every time I've been on a date. and she told me, "You're really a nice guy, and you'd make a great boyfriend, husband, but unfortunately, there's just nothing there. There's no spark." Tell you what, I've been great guide to death. But at any rate, same way for chemical reactions. In order for a chemical reaction to occur, they have to have a certain minimum amount of energy. And that minimum amount of energy is referred to as activation energy. Also on this slide, for the first time, you see an energy diagram. And these are somebody's illustrations that have gone amok and become so important that people have begun testing them, even though they were meant as just as an illustration. So we really need to take some time to look over it. So let me describe what you're seeing here with this. You have an x-axis, and on this x-axis, you have the progress of reaction or time. Then on the y-axis, you have energy. Halfway up the energy axis, you have a flat line. Then you have a hump that goes up and then falls all the way down nearly to the bottom and goes flat again. This first flat part is called the energy of the reactants. If we were to relate it to that hydrogen iodide reaction that we had right here, we'd have our hydrogen here and we'd have our iodine here. Then they form reaction intermediates that are located at the top of the little hump here. The difference in energy possessed by the reactants and possessed by the transition state here, this difference between the reactants' energy level and the top of the hump, that difference in energy is referred to as activation energy. Now, let's look at one other form of energy here. If we look at the difference in height between the energy of the reactants, the first flat portion, the energy of our products, and that second flat portion represents our products. So our 2 molecules of hydrogen iodide would be at our flat portion there. That difference in height is the energy change for the reaction. And we'll look at a couple more of these energy diagrams here. It's very rare for a chemical reaction to leave the energy inside the chemicals at the beginning and end of the reaction the exact same. When we talk about the energy change accompanying a chemical reaction, we are talking about the energy possessed inside the chemical. We're not talking about the energy that you may feel as part of the surroundings. We're talking only the energy inside the chemicals. The heat of reaction is the amount of heat, in other words, amount of heat energy, absorbed or released during a reaction. It is the difference in energy of the energy inside the reactants and the energy inside the products. We give this heat of reaction a fancy symbol when it occurs at a constant pressure. When this heat of reaction occurs at a constant pressure, we give it the symbol delta H. We also sometimes use the fancy name enthalpy for it. But that's just a cool word to drop if you really want to impress people at parties. The change in enthalpy for a reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. In chemistry, we use this triangle symbol here to represent change. Reactions are divided into two different categories based on whether they absorb heat or whether they require heat. An exothermic reaction is a reaction that releases heat. It is a reaction where the products have less energy inside of them than the reactants. This is something that we often find confusing because we're bystanders to a chemical reaction. So an exothermic reaction to us feels hot because we're feeling the heat released from a chemical reaction. In order for us to feel that heat given off, the chemicals themselves have to lose it because energy can't be created or destroyed. So in an exothermic reaction, even though we as the surroundings gain heat as a product, the chemicals themselves lose it. So in an exothermic reaction, the energy of the products is less than the energy of the reactants. Heat of reaction is released. Heat can be thought of as a product. One way to reconcile endothermic and exothermic reactions is to think of this arrow as having to be an equal sign. Whatever is on one side of this arrow has to equal what's on the other side. So if we're seeing 51 kilocalories of energy being produced in this chemical reaction, that means that these 51 kilocalories had to come from inside these two substances. So the chemicals, or atoms or molecules, have lost energy. This molecule of methane has less energy inside of it than did the carbon and the hydrogen separately. There are also two ways to write exothermic reactions. This way, where heat is displayed directly as a product, is the way preferred by biochemists and biologists. You'll see them using that form quite a bit. Other types of chemists, called p-chemists, what they like to do is they like to write a chemical reaction then they'll put a semicolon at the end, a delta H, and then they'll put a negative 51 kilocalories. And whether the reaction is endothermic or exothermic, they'll always place that change of heat of reaction at the end there. But what they'll do is they'll change the sign to let you know whether it's endothermic or exothermic. And I'm going to write this up here so that you don't forget it. Exothermic reactions have a negative change in heat. Why negative? Because the chemicals have lost that energy. Exothermic reactions will always have a negative change in enthalpy. On the ACS exam, which those of you who are taking this online won't take, it's a common question for them just to ask you whether a reaction is exothermic or endothermic based on the sign of that change of reaction. Another important thing that you need to realize when it comes to exothermic reactions involves these bloody reaction diagrams. Once again, these were a teaching tool that people have warped and twisted into something they like testing. But because everybody does it, I'm kind of forced to go along with the party. In an energy diagram here, exothermic reactions, the products have lost energy, right? So the product line will always be lower than the reactant line. So once again, you're going to want to make a note. For an exothermic reaction, the energy line for the products is, and I forgot the most important word, is, let's change color, is lower than the energy line of the reactants. And some of you are saying, I'm beginning to understand those weird garbled emails he sends out to us more and more. Speaking of weird garbled emails, why don't you write down Winnie the Pooh? You should write down Winnie the Pooh. Winnie the Pooh. The opposite of an exothermic reaction is an endothermic reaction. In an endothermic reaction, heat is absorbed. In an endothermic reaction, the chemicals of the product have more energy than the chemicals of the reactant. Therefore, since energy can't be created or destroyed, and we have to view this arrow here as an equal sign, we have to add energy as a reactant. What we're saying is when we say we have an endothermic reaction is the bonds of this molecule have more energy than the bonds of these molecules. And in order for this reaction to occur, 43.2 kilocalories of energy have to be added from someplace. Visually, I think the graphs help you with an endothermic reaction quite a bit. If we look, the energy of our reactants is going to be lower than the energy of our products. Why? Because we had to add energy to it. So we'd have our nitrogen here, our oxygen here, and we'd have our nitrogen monoxide up here. Our reactants have less energy than our products. Once again, endothermic reactions can be confusing to us as spectators. In an endothermic reaction, our chemicals gain energy, but we're not part of that reaction process. We're part of the surroundings. So when we touch an endothermic reaction, it's going to feel cold to the touch. It's going to feel cold to the touch because it's taking heat from us, right? In order for it to gain that 43.2 kilocalories, it has to gain that energy from somewhere. One possible source of energy is us, right? It's going to steal our heat in order to make the reaction go. So endothermic reactions actually feel cold to the touch, even though the chemicals are gaining energy. Heat is absorbed. Heat is a reactant. So if we're writing it in terms of the way biologists like to write things, all right. So if we're writing things the way biologists like to and biochemists like to, we'd write it with heat as a reactant. If we were writing it like p-chemists like to, we'd write our chemical reaction just like we did before. And even though heat is a reactant for this equation, we're still going to put our semicolon here. We're going to put our delta H at the end, even though heat's a reactant. But people are going to know it because our change in the heat of the reaction is going to be positive because our chemicals are gaining energy. So for an endothermic reaction, your change in heat of reaction is going to be positive. Also, just to make sure, on an energy diagram for an endothermic reaction, the products are going to be higher. Their product line is going to be higher than the reactants. And if we zoom in on it, since this is our first time really looking at it from an endothermic perspective, you go away. All right, there we go. If we look at it from an endothermic perspective real quickly, notice our activation energy is still the difference in height between the energy of the reactants and the top of the hump. The energy of the products is still the difference in height between the product line and the reactant line. Good? Because I know people like summary slides, so I threw it in here. Learning check in the house! Identify each of the following reactions as either exothermic or endothermic. Pause me and try it yourself. Did you pause me? Did you pause me? Did you pause me? Thank you for pausing me. I appreciate it. You will have benefited from having done so. All right. First, it's really basically pretty simple. Whenever we see energy as a reactant, and whenever we see energy as a product, whenever we see energy as a product, we know it's exothermic. So in our first one, we see energy as a product, and in our third one, we see energy as a product, so we know it's exothermic. Then, in our second one, energy is a reactant, and whenever we see energy as a reactant, it's endothermic. Chemistry's easy, life is hard. All right, let's talk about the math we can do with the heats of reaction. It turns out when we write heats of reaction, the quantity of energy that we're writing is in molar relationship to the chemicals in the compound. Meaning, for this reaction that we're looking at here, that for every 1 mole of nitrogen I react, I need 43.2 kilocalories. For every 43.2 kilocalories of energy I react, I can produce 2 moles of nitrogen monoxide. This means that I can use a chemical reaction and this heat of reaction here to give me the molar relationship between substances and energy. For example, from this chemical reaction, I know that 1 mole of nitrogen is equal to 43.2 kilocalories. And knowing that, I can go from either energy to moles or moles to energy, right? I have 2 different conversion factors. It gives me the relationship between oxygen and energy. And it's important to realize this is in the context of this one reaction, right? The relationship between oxygen and energy would be different in every single reaction you're doing. These energy values are reaction specific. I know the relationship between energy and my nitrogen monoxide. I know that 2 moles of nitrogen monoxide are equivalent to 43.2 kilocalories of energy. So I can get two relationships from that. And you know, all this talk of moles, there's only one thing that would be appropriate for you to write down with all this talk of moles. Fantastic Four. You have to write down Fantastic Four. Matter of fact, I got so distracted by Fantastic Four, I forgot my nitrogen there. And I made it nitrogen dioxide. Wow. Not a lot of sleep last night. All right. So a chemical reaction gives you those relationships. And the great thing is, if you have that relationship, that means you have the ability to do some stoichiometry with it, which is exactly what we're going to do here. For example, if I have (172.8 kilocalories of energy and excess nitrogen and oxygen, how many moles of nitrogen monoxide can I produce? Well, I have no idea how to work this problem. I'm getting panicky. And then I remember, hey, wait a second, I just need to get rid of whatever unit I'm starting with. I've only got one number and it has kilocalories attached. So I know that whatever unit I have here, I'm going to automatically place down there. Do I know a relationship between kilocalories and nitrogen monoxide? Yeah, my chemical equation down here gives me one. It tells me that 43.2 kilocalories is equivalent to 2 moles of nitrogen monoxide. Hey, moles of nitrogen monoxide are what I'm looking for. So I just need to multiply everything on top, divide through by everything on the bottom. And that gives me 4 moles of nitrogen monoxide. Or at least it should if I did my math correctly. Let me check myself before I wreck myself. No. I utterly and completely goofed. I can't do simple math today. I should really just rearrange that. But I thought it was necessary for me to prove that I am indeed human, because some of you have already begun to think that I am something much more remarkable than human. So, it was actually 8 moles, right? When I multiplied everything on top, divided through by everything on the bottom. So I produced 8 moles of nitrogen monoxide. I can do it the other way, for example. If I have 0.5, well, let's keep the numbers simple here. If I have 0.50 moles of oxygen and excess nitrogen, how many kilocalories if I have 0.500 moles of oxygen and excess nitrogen, how many kilocalories would I need to convert all of my oxygen to nitrogen monoxide? And that pretty much wins the award for the most awkwardly worded question of the year. No, Dr. Kelly, we've heard you word things much more awkwardly. Thanks. We've got one number in the problem. So once again, even though we have no idea how we're going to solve this, we know that our first thing that we're going to do is get rid of the units attached to that one number, which happen to be moles of oxygen. Do I know anything about moles of oxygen and kilocalories? Yeah. My chemical reaction tells me for every 1 mole of oxygen, I need 43.2 kilocalories. So 1 mole of oxygen, 43.2 kilocalories. Hey, I now have the unit that I'm being asked for in the question, so I must be done. So I multiply everything on top and divide through by everything on the bottom. And that gives me 21.6 kilocalories. And that's all there is to it. Fantastic. Ooh, now I'm thinking about the Ninth Doctor. Everybody write down the Ninth Doctor. Everybody write down the Ninth Doctor. And if you haven't watched Doctor Who, shame on you. All right. Learning check in the house. Let's kick the party up a notch. Instead of just doing simple one steps, let's throw a little bit more fun on the fire. How many grams of oxygen react if 306 kilocalories are released from the following reaction? All right, I can see that I've got one number to start my problem with. So I have 306 kilocalories. I know that whatever I'm going to do to solve this is going to involve canceling out those kilocalories. Do I know anything about kilocalories and the relationship to oxygen? Well, I look at my chemical reaction, and I see that for every 213 kilocalories I produce, I need 2 moles of oxygen. So, according to my chemical reaction, 2 moles of oxygen is equivalent to 213 kilocalories. So my kilocalories have been canceled out, and I'm left with moles of oxygen. However, this time they're not wanting moles of oxygen. So I know I'm going to have to do something to get rid of those moles of oxygen. So once again, I don't need to think. I don't have a unit I want, so I know I have to get rid of it by placing it down there where it cancels out. Well, happily, the periodic table tells me that 1 mole of oxygen is 32 grams of oxygen. Hey, grams of oxygen is what I'm looking for, so I must be done. So I just need to multiply everything on top, divide through by everything on the bottom. I get a calculator lie of 91.9436 gobbledygook. I look at my sig figs. They gave me 3 sig figs here. They gave me 3 sig figs there. That's exact. The 2 from our chemical equation. Really, our periodic table, I got sloppy there. It should be 32.00 based on the one that is in your book. So that gives you 4 sig figs. So my least number of sig figs is 3. 1, 2, 3. Cha-cha-cha. So we've got 91.9 grams of oxygen. Chemistry's easy, life is hard. Whatever. That's it. Beep.